independent Gaussian random variable. So what I argued a little bit is that this is a beautiful definition, but it's not completely rigorous because the way of writing it would imply that the psi is a random function, right? It takes some value, some space-time point Tx and maps it to some random value in R. This is what it would imply. Unfortunately, this does not work. So the only way we can rigorously define it is as a random Schwarz distribution. So this means that actually its domain are Schwarz functions. So functions that are smooth, so C infinity, and decay quite fast at infinity. And the way to define then the correlation structures in this way. So the expectation of psi f times psi of g is the L2 scalar product between f and g. So that's the rigorous definition. What we also saw is in the specific case where the space is R and not R times RD, space-time white noise actually is the derivative of the Brownian motion. Yeah? Which already kind of says that, well, it's not it can't be a random function because, as you know, Brownian motion is not differentiable in the classical sense, but only in a weak sense, in a distributional sense. Okay. So this was the part about the space-time white noise. And then we studied some properties. And the first one was the property that we studied is we checked under which scaling white noise is scale invariant. So this makes sense because, well, we know that for Brownian motion, for instance, a lot of properties we can already deduce or guess from its scale invariance. So the same we try to do in this case also. And what we saw is that, heuristically at least, we have this behavior. So if you rescale time by tau and space by lambda, yeah, then this process in law coincides with the original space-time white noise, however, with a prefactor tau to the -1/2 and lambda to the -d/2. In the case of Brownian motion, I already argued that, well, the space would not be there, that the factor would be tau to the 1/2. So that's what we all know. But because you take a derivative, kind of you lose 1. So the 1/2 becomes 1/2 minus 1, minus 1/2. Okay. So then the next level of difficulty was to look at the linear stochastic heat equation. So this equation. For this equation, you can also ask yourself, under which scaling is it scale invariant? And it turns out that if we define a new process z hat in this way, that z hat of Tx is lambda to the d/2 minus 1 times z of lambda squared times t, lambda times x, then this process coincides in law with z, with the solution to this equation. So you see, if you look at space-time, you need to scale diffusively, space by lambda, time by lambda squared. So that's what we kind of know also from the central limit theorem. And but we additionally did this factor here. Okay. So the next level of difficulty is now to look at the so-called Kpz equation, which is this equation here. So if you compare the Kpz equation, this equation with that equation, the only difference is the nonlinearity. If you ignore the nonlinearity, it's the same equation. And so this motivates the following question. So what is the big difference between the linear equation and this nonlinear Kpz equation? So in particular, how important is the nonlinearity? Does it dominate in small scales or not? Yeah? And so the way to see it or to investigate is, so here we restrict ourselves to dimension 1. Yeah? So this d here would become 1. So it would be 1/2 minus 1, so minus 1/2. To rescale the solution to the Kpz equation in this way, lambda to the -1/2 time scale by lambda squared and space by lambda. Yeah. So then you can do some computations, and then what turns out that this h hat satisfies this equation. Yeah. So what you see here on the right-hand side, the Laplacian is untouched. The noise is untouched. It's actually a different noise, but still white noise. And what happens with the nonlinearity? Well, we have this factor lambda to the 1/2 in front of it. So at least formally, as lambda goes to 0, yeah, so this means looking at the small scales, formally as lambda goes to 0, the nonlinearity vanishes. So this means that on small scales, heuristically at least, it seems that the nonlinearity is only a perturbation of the linear equation. And whenever that happens, we call such an equation subcritical. And in this regime, we are allowed to apply the theory of regularity structures. In these cases, you can apply the theory, then it works. Okay. And okay, so this is essentially the summary of the first class. And today, what I would like to do is to talk about regularity. So the theory is called theory of regularity structures. So at some point, we need to talk about regularity. And this is what we're going to do today. So the first part may be a bit boring because what I need to do is I need to define what I mean with regularity. Yeah. But well, let's go. Let's do it. Regularity. And so there's a convention that is quite helpful, is that the type of norms that we look at. So we define the parabolic distance, z minus z prime s between two space-time points, between z and z prime in R times Rd, with, let's say, z is of the form Tx, oops, is of the form Tx, z prime, let's say, is of the form T prime, x prime, via the following formula. Z minus z prime s is what is the square root of t minus t prime, or the distance between t and t prime, plus the sum j from 1 to d xj minus xj prime. So whenever we want to measure distances in space-time, we will use this norm. Okay. And so let me state a fact. So under this norm, oops, or under this distance, well, this norm, let's say distance. So a ball of radius r has volume of the order r to the d plus 2. So if you compare this to the usual volume, say if this 1/2 wouldn't be there, if this 1/2 wouldn't be there, then the volume would be of the order r to the d plus 1, right? This kind of means that this time dimension counts double under this distance. And so I would like also to explain to you why this is done. So this is not crucial for the theory in the sense that the theory breaks down if you don't use this distance, but it makes a lot of expressions much more nicer, much more clean. Yeah. So why do we do this? So I mean, why do we measure distance in time different to distance in space? So the question, why do we use this distance? I mean, why does it make sense? Well, answer. So our equations are of the form. Well, so we always have something like dtu, say, equals Laplacian of u plus something. This is the equations we will now look at, plus some stuff. Yeah. So what does this mean? So here on the left-hand side, we say, well, the first derivative in time equals the second derivative in space plus something. Yeah? So this really means that, so one derivative in time has to be equal to two derivatives in space plus something. Derivatives in space plus some stuff. Lower order derivatives, okay, at most. Yeah, so one derivative in time really equals two derivatives in space. And so this kind of justifies that probably you need to treat space and time slightly different. And because of that, we take a 1/2 here and 1 here. So here's the double of that. That's essentially important. You can also take a square here and 1 here. You could also do that. Okay. Okay, so if you accept that we use this kind of funny distance, what we can now do, we really can start to talk about regularity. And we can talk about Hölder spaces. So let's recall kind of the usual Hölder spaces where alpha is between 0 and 1. Yeah, so what was this space again? So definition. So for some alpha between 0 and 1, so C S alpha of R times RD is the space of all functions, U mapping R times RD to R, such that what holds? Let's say a locally Hölder, such that, say, for all compact sets K of R times RD, yeah, the supremum over all Z prime and K that are not equal, the distance between U of Z and U of Z prime divided by Z minus Z prime to the alpha is finite. So this is kind of the usual space of, well, it's not the usual space maybe, but that's the space of Hölder continuous function where alpha is between 0 and 1 using this norm. Yeah, where we treat time and space slightly different. Yeah. So what this really means is that when Z approaches Z prime, say, so this distance here will go to 0, and we can even determine the rate. It goes to 0 like the distance between Z and Z prime to the alpha. Okay. So this is nice. But if you think of the things that we want to study, I mean, we want to study the stochastic heat equation, right? We want to understand white noise. So I already said that white noise actually doesn't make sense as a random function, but only as a random distribution. So it makes sense to look at negative regularities. So actually what we would like to do is we would like to look at the same spaces, but with negative alpha. Yeah. So naively, you could say, well, okay, you just choose the same definition. Yeah. But of course, the initial problem is already that if we think of negative alpha, we don't think of functions. So U of Z may not make sense, but we really think of objects that you need to test against smooth functions.
Yeah? Dirk?
Yes.
I didn't understand this part because, well, alpha negative makes sense, no?
Okay, so if you, okay, it depends, of course, what you want to do with alpha negative. So what we want to do here, when we think of alpha negative, actually we want to think of regularity of a class of distributions. Of course, if you take a function U, you can define this for alpha negative. There's no problem. But okay, now we would like to look at the regularity of distributions.
I see.
So alpha negatives should already mean that something is not really regular. And we kind of want to quantify how regular it still is. It is not regular, but maybe there's a certain degree still of regularity, which is not good, but well.
But for functions, what does mean alpha negative in this supremum? It's blowing up, right?
Yeah, it would be that's blowing up. So
I
actually,
see.
it does not make much sense if you take a continuous function. It does not make much sense.
I see.
I mean, so well. Of course, you can choose this definition with negative alpha, and then once you have a continuous function, it will be in this negative alpha space. Trivially somehow. Okay. So what we need to do is kind of need to try to find kind of a similar definition, but when instead of evaluating our object at fixed points, we need to test them against the functions. Okay. So maybe you can stay. So notation. So for R positive, so what we will do is define a space BR. This is essentially now our space of test functions. R to the D plus 1 to R, such that they have a compact support, say in the unit ball. Yeah, so this here is the unit ball. B1 of 0 is the unit ball. And say with a bounded CR norm. Okay. Less than 1, for instance. Okay. And so now the definition that we will use for this negative C alpha space is the following. So suppose that alpha is negative. Okay. So we define CS alpha to be the set of all distributions, to be the set of all distributions U, all Schwarz distributions, sorry, as R times RD, such that for all compact sets in R times RT, we have the following. We want that this object is C as alpha of K, which is what? The supremum over all Z in ZK, the supremum over all admissible test functions, BR, over all lambdas between 0 and 1, excluding 0, of testing your function U, your distribution U against SZ lambda of eta, which I still need to explain what it is, divided by lambda to the alpha is smaller than infinity, where R is the integral part of minus alpha. And, okay, so I said that this part will be a little bit boring, but it's life. So what is this SZ lambda? So this SZ lambda, what it does is the following. It kind of recenters my test function eta. Yeah. So it recenters my test function eta around the point Z, if Z is given by Tx, y minus x. Yeah. And it rescales this function. So where here time is rescaled by lambda to the minus 2. Sorry. Lambda to the minus 2. And space is scaled by lambda to the minus 1. If you do this, so you could do this. So what would happen? So let's just focus on this guy here. And let's think of lambda very, very small, okay? Let's think of lambda very, very small. This eta here has a compact support. Okay. So this means that, for instance, this thing, lambda to the minus 2 times S minus T must be of an order smaller than 1. So this means as lambda goes to 0, S minus T must be of order less than lambda squared. So as lambda goes to 0, essentially S must be equal to T. So as lambda goes to 0, this function essentially vanishes, except at the point T and X. And well, what you want to guarantee is that at least, so this is a fact of life, this will happen, But what you would like to guarantee is that at least the integral of this function stays constant. And it stays constant if you blow it up. Yeah? So this function here, this factor here in front, lambda to the minus d minus 2, guarantees that this object as z lambda eta has an integral that does not depend on lambda, that is really constant for all lambdas. Yeah. Okay. Okay, so again, so here we do a recentering. We center this function around eta, and then kind of we shrink the support of this function. So what is really happening is, says if here's this point z, as lambda goes to 0, this function may look like something like this, with a constant integral, where this height is of the order lambda to the minus d minus 2. Okay. Okay. So what do we do here in this, in the definition of this norm? Well, here we have our distribution. We test our distribution against this kind of rescaled function. So what is this function again? So this object here, we need to think of lambda being small. This object here has a support centered around z. Yeah. And the size of the support is order lambda, and lambda goes to 0. So the support really is concentrated around this point z. Yeah. And if u would be a continuous function, this object, as lambda goes to 0, actually would converge to u of z. Yeah. So observation. If u would be continuous, and I probably need this, and let's say the integral of eta is equal to 1, but it's a minor thing, then this thing here is that lambda eta, right, which is just this integral in this case, is that lambda eta of x dx, this would really converge to u of z. Yeah. Simply because when lambda goes to 0, if x is not extremely close to z, this thing is simply 0. Yeah. And if u is continuous, well, if x is very close to z, u of x is essentially equal to u of z. And now we chose the rescaling with this rescaling operator such that it leaves the integral of eta constant. Yeah, so is this clear?
I have a question. Mm-hmm. So if u is continuous, mm-hmm. we can integrate it against a function, so it gives a distribution. Mm-hmm. What's the regularity of this distribution?
0.
0, because when you divide by lambda to the 0,
nothing happens. Exactly.
Exactly. It works. Okay.
Exactly. So you see, if you have a continuous function, then you can reapply this definition, and with this definition, alpha would be 0, because, well, this thing simply converges to the value of u of z. However, if u is a distribution, then of course you are not allowed to evaluate u at a fixed point. So what should happen is then that this thing actually will explode at a certain rate. It will explode at a certain rate. And this really captures the rate at which it explodes. So for negative alpha, somehow this alpha is a measure of for how far u is away to be a continuous function. Yeah. So how much this guy actually explodes. Okay.
Dirk?
Yes.
So I just missed the definition of your approximation of the identity eta.
It's like this.
Yeah, so eta, you said that eta belongs to B gamma.
BR. So this is essentially the space of test functions, which are in CR with the bounded CR norm and have a compact support.
Ah, okay, perfect. So you're taking the supremum over all approximations identity with which are sufficiently regular.
Exactly. Yeah, exactly.
And that
And you
works
can-
as a norm.
Yeah, this works. Yes. Wait, so it works as a norm. I guess so.
No. Okay, thank you.
Okay, so that's it. And now essentially, okay, so if you compare these two definitions, kind of the classical definition of alpha Hölder spaces, with these definitions, I mean, they have certainly some similarities, but they're also a bit different, right? Because so here we need to go to test functions. Here we do point evaluations. So what would be maybe desirable to have kind of a unified definition? So that's simply a bit more convenient in applications. It's not completely necessary, but it's a little bit more convenient. Yeah, Christian?
Trivial question. C menos alpha is the dual space of C alpha?
Yeah,
Oh, no.
I think so. Yeah.
Okay.
Okay, so what now would be desirable to have a definition for these positive alpha Hölder spaces that is maybe similar in spirit to these guys here. Yeah, simply it makes it much more convenient when you really want to apply it, that you don't need to jump between kind of two definitions, but essentially you can use always the same kind of definition. It's a bit for convenience. And it's of course also a nice exercise to try to understand this thing a little bit better. So what I will now next do, I will give a definition for the positive alpha spaces, another definition which is equivalent to the one I gave, yeah, which takes more this form. So let's see. We go similar definition, which of course coincides with the usual one. Definition for positive alpha. Yeah. So here you will see in a moment why I need to introduce a so-called parabolic degree. So here for multi-index, so for minus the dimension for k in n times n to the d, yes, d plus n to the d. So this thing is 2 times, so say k equal to k0, k1 up to kd, where k0 kind of the time direction is equal to 2 times k0 plus the sum j equal to 1 to d of kj. Yeah. And so z to the k, which is really z0, t to the k0, x1 to the k1, xd to the kd for z of the form tx. Yeah, has degree ks. Has degree ks. Yeah, so when we talk about polynomials, the time direction, kind of the degree in time direction, also counts double. Yeah. So you will see in a second why. Okay. So now let's try to introduce a definition which is kind of the same as for the negative alpha spaces, just for positive alpha. So let alpha be positive or larger or equal to 0. So we define C as alpha to be the set of all functions, to be the set of all functions Well, such that for all compact sets in R times RD, this norm here, U C S alpha of K, which is again the supremum over all points we could center our test functions around. The supremum over all continuous functions, let's say. B0 is really the continuous functions for compact support and bounded by 1, let's say. And the supremum over all scales lambda, yeah, of U as that lambda eta divided by lambda to the alpha is finite. Okay. So the fact that here's a huge gap and here's a huge gap probably means that it's not yet the definition that we really want to have. But I mean, if you accept this for now and you compare it to the definition we had above, yeah, then it's literally the same, right? Okay. So why is there a huge gap here actually? So why is there something missing? So let's assume that this would be really the proper definition. Yeah. So problem, let's assume this is really the correct definition. And I don't know, let's say, so U, let's say in C1/2. So what would it mean? It really would mean that something like this U of X as Z lambda eta of X dx, that this is really of the order lambda to the 1/2 as lambda goes to 0. Yeah. But what do we also know? I mean, if U is 1/2 Hölder in the usual sense, and this is what the definition should capture, yeah, then we also know that this is actually of the order U of Z. Yeah. So what does this mean? This actually means that U of Z must be 0. This is clear. If this would be the definition.
Okay, and because it's in the usual definition, it appears a difference, right?
Exactly, exactly. So this can't be the correct definition because it would force our functions to be simply 0. And well, I mean, they're more Hölder continuous function than the 0 function. So definitely this can't be the correct one. So if, of course, we think of continuity, we don't think of functions that are 0, but kind of functions that if you fix a point Z, that the function doesn't vary a lot around this point Z, right? So actually continuity always has to do with comparing the function U at 2 different values that are close to each other. So here, what we really need to do, we need to subtract something. Yeah. In the case, if we want to have alpha between 0 and 1, we would need to subtract here U of Z. If we want to have alpha, say, strictly between 1 and 2, we would need to subtract kind of the first order Taylor polynomial. Yeah. So U of Z plus, well, the first derivative. Okay. This is how you would do it. Of all functions such that there exists a family of polynomials, Pz, so they're indexed by the center, R times RD, yeah. Each of parabolic degree less than alpha, degree less than alpha, such that for all compact sets, okay, U minus Pz. This is fine. Yeah. So this actually makes sense now. And what is this Pz? This Pz is really it's a Taylor polynomial. So remark.
Dirk?
Yes.
So in this definition, do you need to assume some regularity on the choice of these polynomials Pz or no?
But the polynomial is not a C infinity.
No, I meant when you move Z.
No.
But in the definition, the polynomials depend on
On
you.
Z. On Z. Yeah. Actually, you can give a formula for these polynomials, the Taylor polynomials of Z.
Okay.
Of you. Yeah. So in this way, they're no. Sorry. So the Pz must be the Taylor polynomial of order integer part of alpha of u centered at Z, Yeah, so this is really what it is. So there's no magic behind it. Yeah. And this maybe going back to the original definition. So these definitions really coincide for alpha between 0 and 1. Going back to the original definition, of course, you can also ask yourself how in the usual framework you can define Hölder continuous function for alpha being larger than 1, between 1 and 2, for instance. If you choose naively this definition, then you have constant function. That's not very interesting. So then in this case, actually would need to compare u of z with this first order Taylor polynomial. This you could do, or you require that its first derivative is alpha Hölder continuous, alpha minus 1 Hölder continuous. Okay. So anyway, so these are the spaces that we will work with. Are there any questions? Okay. So in this case, what we will do now is actually the same that we did last lecture. So first we look at the regularity of white noise. Then we look at the regularity of the stochastic heat equation. And then we see what it implies for the Kpz equation. I probably will not do everything today, but at least we will start. So regularity of white noise. Regularity of white noise. Okay, so I mean, first of all, before we do any computations, of course, we need to have some idea what will be the regularity. Essentially, we need to have an idea if the regularity will be positive or negative, right? Because if it's negative, then the only thing we need to do is we need to take a sufficiently smooth test function with compact support and test our white noise against the sky and see how it explodes with London. If we think that alpha must be positive, well, then we need to find our polynomials. Well, since we know the dimension 1, white noise is nothing but the derivative of Brownian motion, which does not exist in the classical sense, it's a good guess that alpha must be negative. So the only thing that we really need to do is take our white noise and test it against these guys. Okay. So we do this. So we'll investigate Xi tested against such a thing. Yeah. And so what can we do? So I will not provide the full proof. This is kind of the rigorous proof essentially follows the proof of Kolmogorov's continuity theorem. It's essentially really the same. But I will kind of show you some computation which kind of strongly suggests what is the correct regularity. So since Xi is Gaussian and we know its correlation, so what we always can try to do is to compute second moments. Right? So this we can do. So what we know is this actually is just the L2 norm of this guy. So this is the L2 norm. So it's the integral of SZ lambda eta of Z prime of SY squared. Right? So that's what it is. And so that's now a concrete integral, and we need to figure out what is behavior in lambda as lambda goes to 0. So we can use the definition. So there was this funny scaling factor in front. Since it's squared, it becomes lambda to the minus 2d minus 4. Yeah. And then what we have here is lambda to the minus 2, s minus t, and lambda to the minus 1, y minus x squared, ds dy. Yeah. Okay. So that's really what it is. And now what you can try to do is you can do a change of variables, kind of to kill this lambda to the minus 2 and the lambda to the minus 1. So you do a change of variables in space and time. If you do this, then the minus 4 becomes minus 2 because kind of in the volume factor becomes lambda squared. And if you do this in space, so you get a volume factor of lambda to the d. So the minus 2d becomes a minus d. Yeah. And then here you really have the L2 norm of eta. Yeah. So what this really says sense. So this object here, what is it? Psi s lambda eta squared. This is what? This is lambda to the minus d half minus 1 squared times, well, the L2 norm of eta. Yeah. Which, because its compact support is bounded by some constant times the supreme norm of eta. So that's what you have. And okay. So what it really suggests is that this object here, as lambda goes to 0, blows up like lambda to the minus d half minus 1. Yeah. And so the nice thing is, since this is Gaussian, you can essentially show the same without effort for all higher moments. Fact. So it's maybe it's something very convenient to know. So if you have something Gaussian, x Gaussian, yeah. So then for all p's, I'm not sure if they need to be integer or not. There exists a constant Cp, so which does not depend on the Gaussian random variable, only on p, such that the pth absolute moment of x is bounded from above by this constant times the second moment to the p half. Yeah. So if you formally do the multiplication 2 times p over 2, it gives p. So it's kind of the right thing. Yeah. So what does this imply? So this implies that, okay, here we did a second moment computation, but it all immediately gives kind of the behavior of all higher moments without that we need to do anything. Yeah. So hence, all the higher moments really behave in the same way. To the p. So this is less or equal than lambda to the p times minus d half minus 1. Okay. So was this clear? Okay. Check. Okay. Okay. So maybe Guilherme is a good exercise to check that the Dirk distribution really has the regularity of minus space.
This was easy.
Okay.
But I'm trying to check the calculations. In the on the second moment is the norm of eta to the squared, right? I believe that doesn't matter, but
okay, maybe this is squared. Yeah.
And so you put out this 2. Can you go down?
Sure. More.
So to the p moment, you just use. Okay. Yeah, it's clear. Thank you.
Okay, great. Perfect. And now, I mean, I will now not give the full rigorous argument, but kind of following the proof of this Kolmogorov continuity theorem, what you can show is that white noise has regularity almost minus d half minus 1. Yeah. Yeah. So with a bit more of work, what you can show is that the psi is an element of CS alpha for all alpha smaller than minus d half minus d half minus 1. Yeah? Okay. So if you now we can think a bit about it if it's reasonable or not. So let's assume we have white noise only in one dimension. Yeah? So in this case, we know it's a derivative of Brownian motion. So this would be the case where, let's say, the one would not be there. We only have one space dimension. So then we would have a minus 1/2 here. Brownian motion is almost 1/2 Hölder. So if you take the derivative, it should be almost minus 1/2 Hölder. Yeah. So this heuristic suggests that in one dimension for d equal to 1 and there's no time, that the regularity should be a bit less than minus 1/2. And that's exactly what we observe here. So this is kind of another sign that the choice of spaces is good. Yeah.
The regularity of the Brownian motion it's what's the 1/2?
It's 1/2 minus. So it's 1/2 minus epsilon. This you see actually also from the scaling, yeah?
Yeah. And the computation goes by the moments also.
Yeah, exactly. Yeah. Okay.
But when you take the derivative, so in one dimension, we lost -1.
Exactly. Which is reasonable, right? You take one derivative, so you should lose one in regularity. Yeah. So this really shows that the spaces are kind of well chosen, so they're not completely crazy. More questions or comments? Okay.
Sorry. Go ahead there, Guilherme.
No, the proof of the regularity of the white noise is similar to the Brownian motion. I mean,
yeah. I don't remember completely, but yeah, it's very similar. Okay. I think it's in the notes that I was mentioning last time. Maybe not up to the last epsilon, but it's pretty convincing.
Thanks.
Okay, Dirk, just to be so the definition of C alpha you're giving with this kernels is not exactly the same as the definition of C alpha people is used to, no?
Why?
No, because I mean, in principle, is your norm is larger than the usual one, no? Because in the usual one you don't have this supremum over all these test functions, no?
I think there. I mean, of course, everything I learned here is from Martin, but I would guess that in the usual, I don't know what that. Of course, what is important here that the norm of eta is, I mean, the infinity norm of eta is 1. Otherwise, I think there's no way that this is bounded. Otherwise, you could kind of multiply eta by whatever constant, and then this explodes, of course. So what is, okay, so this is one way of defining it. And now, I mean, it's reasonable. So now you, for instance, if you want to do some, maybe that's actually a very good comment. So of course, if you want to show of a random object that this norm here is finite, I mean, then you really have a problem, because here at least you have the supremum over all these test functions, which is an uncountable set. So it's huge. I mean, how do you take the supremum out? But it turns out that actually you can replace the supremum by a countable set of functions that are kind of behave, where actually there's only one mother functions and all the other functions are built from that function through a rescaling procedure. Yeah. I'm not sure if this helps. But yeah, so my feeling is that all of these norms are kind of, I mean, up to maybe some constants or so, but that these spaces all coincide also with these different definitions. Except, of course, for values of alpha that are integer values.
Yeah.
Okay. Okay, so great. So now we have studied the white noise. And so now, like last time, we will now go to the linear stochastic heat equation. So let's try to understand this before we go to any nonlinear equation. So linear theory. So the equation that we want to study, that we want to consider, is the following equation. So dtu is Laplacian of u plus some f, and started from some initial condition, which actually I will put equal to 0, simply not to have to bother with this. So what it turns out, there's something called mild solution or Duhamel principle, which is what I will write down now. So we can take it as a definition of Duhamel's principle, or as a consequence of it. U of tx is what? It's the integral from 0 to t. So let's assume that here space is in the torus. The integral over the torus of k of t minus s, x minus y, f of s y, ds dy. Yeah. So what this here is, I will still explain what is k, but k will be the heat kernel. So this will be the convolution of the heat kernel with this with the right hand side f plus the initial condition. So the integral only in space k of t x minus y u0 of y dy. Yeah. So that's one way to represent this solution. Yeah. Okay. And so this is really the solution we will work with. And as I said, so here k is the heat kernel on the torus. Here k is the heat kernel on the torus. Yeah, so which is, I don't know, r over minus p pi pi to the d. Yeah. And actually it has a precise representation. So k of tx is what? So that's the sum over all L in 2 pi zd of 1 over 4 pi t to the d half exponential minus x minus L squared over 4t. Yeah, so this is the heat kernel of the torus. So what will come, I will most of the time really ignore the sum, because it turns out that the heat current on the torus and on the one of the full space, they have the same properties. So I will usually try to ignore this. Okay. So what we now would like to do is we would like to understand now this guy U. So in particular, we would like to understand that given F, what is the regularity of U? Yeah? And of course, the particular F that we're interested in is the white noise. We already know the regularity of white noise. So now we would like to know what is the regularity of U given that F is white noise. To simplify the computations a little bit, I will assume that U0 is 0. Okay. So assumption. So U0 is 0. And the question is, what is the regularity? The regularity of U when F is psi is the white noise.
Dirk,
Yes.
why do you need to go to the thoughts?
So as I was saying, so when you regularity structures, actually for this computation that I will do now, it's not actually necessary. But regularity structure is a local solution theory. So its full strength only works on a compact space.
I see.
But for what I will do now is actually not necessary. And actually, you will see, I will actually pretend that this case, the heat from the full space.
Okay. Okay. Thank you.
Okay, so now, so we assume that F is equal to the white noise, and we would like to know what is the regularity of U. So let's check a little bit what is happening here actually. So in this equation, to formulate this equation, I mean, we have this dtu, so the derivative in time, we have this Laplacian of U, two derivatives in space. So this kind of implies that we need to be able to form a derivative in time and two derivatives in space. So this heuristically, or at least it's not completely crazy, maybe it's wrong, but it's not crazy, is that at least in space, the solution U should have two more regularity than the white noise. And in time, the solution should have one more regularity than the white noise. And since we are looking at this weird parabolic scaling where one derivative in time equals two in space, it turns out that the solution to this equation has two more regularity than white noise. So claim, and this is what we try to prove, U is the Hölder function with what is the regularity minus d over 2 minus 1. So remember, this is the regularity of white noise, actually not quite, it's a little bit less. And this, and U has two more regularity, minus. So this minus comes from the fact that the white noise does not have quite this regularity, but this regularity minus epsilon 4 in the epsilon. Okay. So really, I mean, really the moral behind the story is U has two more regularities than the white noise. Okay. So let's make an observation. So minus d minus 1 plus 2, let's compute some values. So if d is equal to 1, so then this is 1/2, right? If d is equal to 2, so then this is 0. And well, if d is equal to 3, it's minus 1/2. So if d is equal to 3 or larger, then this is less than 0. Yeah. So really seems that the higher the dimension, the worse the situation gets. Which makes sense because, I mean, this guy has a worse regularity with higher dimensions. Okay. There's also another consequence is that remember that for positive alpha and for negative alpha, actually, we needed to use slightly different definitions, right? If we want to prove a negative regularity, then we need to use that definition. So
I have a silly
Yes.
question.
Sure, go ahead.
Why the regularity? What's the intuition for the regularity becoming worse with the dimension?
Okay. Because you can kind of imagine, so if you're on one dimension, the white noise is derivative of Brownian motion. And then somehow, if you add some dimensions, in the sense that it's like you're adding derivative. It's like, well, maybe imagine that you have something like a d-dimensional Brownian motion, and now you kind of take derivative in each of the coordinates. So every time you lose something. Maybe that's a good intuition.
I see.
You're kind of irregular in more and more dimensions. So there's no kind of dimension that kind of where you gain regularity. Actually, in each dimension you lose regularity, and all this adds up.
I see.
Yeah, I don't know. Do you have a better explanation? Or Christian? Okay. Anyway, so if we want to prove negative regularity, we need to use this criteria. If you want to prove positive regularity, I mean, positive regularity again really means that your function is varying only little around, well, some polynomial or around a certain point u of z. Yeah. So then we really need to subtract Taylor polynomials here. Okay. So this we need to keep in mind. So in particular, what this means is that in dimension 3 and higher, the object we need to look at is different from the one in dimension 1. Yeah. Okay. Okay, so let's do the computation. And so this is a great moment to introduce graphical notation. So if you look at this paper of regularity structures, then they have all kind of these horrible graphs. And if you're not used to this, I mean, that's extremely scary. So when I start to work with this, I kind of try to push this away as long as possible and say, no, 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 I don't need to do this. But at some point you realize that it's really much more convenient to work with this graphical notation. So for that reason, what I will already do, I will introduce graphical notations in this context that we are now, which is a little bit overkill. So in the context that we are right now, this linear equation, there's actually no real need to introduce graphical notation. Things don't really simplify because of that. You know, they only simplify when you go to nonlinear equations where things become more complicated. However, it's a good exercise to already kind of to get used to this kind of notation. Okay. So again, we assume that u0 is 0. So this part is not there. So this solution is what? It's a convolution of the heat kernel with the right-hand side, with our white noise. Okay. And we want to have a graphical notation for that. And these graphical notations, they may change from paper to paper, but the idea is always the same. So you need to check always at the beginning what is the precise convention, but the idea is always the same. So instead of u, or instead of k convolved with psi, we will write this, where this dot here so represents psi, yeah, and this line here represents the convolution with the heat kernel, convolution with k, okay. Okay. So instead of, so again, so this is really k convolved with psi. Psi is this dot, and this line is the k. Okay. So let's try to get used to this a little bit. So I will kind of jump back and forth between really concrete integrals and this graphical notation. Yeah. So really what we need to look at is something like this. We need to take our function u and test it against a scaled test function. Yeah. So what is this? Here really, we have the integral of u of z bar against this object here, z bar dz bar. Yeah. Which in our graphic notation we could also write like this. So this is a valid way of writing this. Yeah, so I just want to emphasize that there's nothing big behind this graphic notation. It's just instead of u, we write this weird symbol. Okay. So now let's try to evaluate this. So what we will now do is we use simply the definition of this guy. So it's k convolved with psi. So let's write it down really what it is explicitly. So you will now see an explicit computation, which is maybe a tiresome, but I think it's good to see it. So with this integral over z bar, and here we have the convolution. So k of z bar minus z tilde, let's say, psi dz tilde, and here with the test function. Okay, z bar. Yeah, I hope this is clear. So this is the object that we try to investigate, and we would like to know how it explodes with lambda. So the next thing that we will do, we essentially follow the steps from the white noise computations. So we will take the second moment, which is actually enough, because u is Gaussian, so the behavior of the second moment determines the behavior of all higher moments. Okay. So by the definition of the white noise of psi, yeah. So what we have here is, oops, S Z lambda eta. So let's see. We need to take the second moment of this integral. So we have 4 integrals. So it gets more and more beautiful, actually. So let's see. So we have an integral over z bar. So this will turn into 2 integrals over z bar 1 and z bar 2. Yeah. Okay, so we have here an instance of k. So this will also get doubled. So we will have 2 instances of k. One evaluated z bar 1, z tilde 1. Another one evaluated z bar 2 minus z tilde 2. Yeah. So this psi also gets doubled, right? dz tilde 2. Yeah. And the test function also gets doubled. The only thing that doesn't get doubled is z. That's our point that we fix. Z bar 1, Z bar 2. Okay, I hope you're kind of able to follow. And what is missing is the expectation, right? Of all this. So this is what we try to investigate. So what is now the observation? Where's the randomness here? Well, the only randomness is here, right? So we need to take the expectations of essentially this product. What do we know about psi? Well, psi is essentially a completely decorrelated field. So if you have evaluate psi at 2 different points, you take the product, then it should give 0. Yeah. Since it's completely decorrelated, it kind of forces dz1 tilde to be equal to dz2 tilde. Yeah. So we lose one integral. So it's good news. So we lose one integral. dz bar 1, dz bar 2, integral k of z bar 1 minus z tilde, k of z bar 2 minus z tilde, And then we have 2 times our test function. Oops. Z bar 1 and Z bar 2. Okay, great. So this is, we have, there's actually one integral missing, I guess, with respect to Z tilde. Let's write it here. So this is the integral that we need to evaluate. We would like to understand how it behaves as lambda goes to 0. Okay. So what do you do now? Well, you stare at it a little bit and you try to figure out, I mean, it's complicated, right? You have 3 integrals. The heat kernel is pretty explicit, but it's not that easy as a function. So now you need to figure out what is really important in order to determine the behavior of this integral. At least if we think of higher dimensions, then we want to have something that blows up with lambda, right? Well, if we think of this heat kernel here, if Z bar 1 is far away from Z tilde, I mean, the thing really will simply decay fast. If Z2 bar is far away from Z tilde, it will also decay quite fast. And these ethers here, they're smooth functions, so there's no problem actually. So as far as Z1 bar is far away from Z tilde and Z2 bar is far away from Z tilde, there's no problem. This integral will be simply finite and nothing will happen because everything is completely smooth. Eta has compact support. K does not have compact support, but kind of almost. So there's nothing that can really happen that kind of screws up this integral.
But now we should know how if Z bar 1 is far away from Z tilde, maybe we need to know the rate to this goes to 0 or something like that.
Well, actually, so what I was arguing is that if Z1 bar is far away from Z tilde, then this function goes quick to 0. And here we have something of compact support. Nothing can really happen. I mean, of course, you need to check this, but on large scales, essentially nothing can happen. What is dangerous, though, is when Z bar 1 is close to Z tilde, because in this case, the heat kernel can explode, right? I mean, if you remember the definition of the heat kernel, where is it? Forget about the sum. I mean, so here we have something, when T goes to 0, there's a real risk that the thing simply blows up. This can happen, right?
It converts to the delta, right? The Dirk.
Yeah. So this thing can really blow up. So, I mean, this risk is really there. So for large space time, it's beautiful. But when it's small, then you may have a problem. And this is the key observation here. The key observation is that in order to understand the asymptotic behavior of this integral, all we need to understand is how this guy here blows up when Z1 bar is close to Z tilde. This is what we need to understand. Yeah. So that's the observation. So K of Z1 bar minus Z tilde blows up, explodes near the origin. Near the origin. Yeah. And this is all what we need to know. This is all we need to know. Of course, I mean, you need to show it, but it's true. That's all we need to know. Yeah. So really what we now need to study is how this guy blows up when their arguments become close. Yeah. And this motivates the following definition. So definition. So given a real number, I don't know, okay, beta. Yeah. So we say that a function g, which is defined on almost all of Rd plus 1, but the origin, yeah, is a kernel of order beta, is the kernel of order beta. If the following happens. If the following object G beta, which is the supremum of all Z in R to the D plus 1 except 0, of the absolute value of G of Z times Z S to the beta is finite. Okay. You can stare at it a little bit. Let's see how much I managed to do. Okay, let's think about this definition for a short moment. Let's think of the situation where beta is negative. Okay, think of the situation where beta is negative. And in particular, if you think of the heat kernel, I mean, it really only has a blow up close to the origin. So you need to think of Z being very, very small. So what this, of course, means is that G of Z is less or equal than Z to the minus beta, right? Yeah. So if beta would be -1, minus beta would be +1. This is what we do. Oh, okay, no, it's the other way around. Sorry. So if beta would be equal to 1, yeah, so then this really would mean that G of Z is of the order less or equal than Z to the -1. So it can still blow up as Z go to 0, but not too fast. Yeah. So here you see the larger beta, kind of the worse the situation is. Okay. No, sorry. Okay, minus beta, exactly. Okay, so with minus beta, the situation changes. The smaller beta, the worse the situation becomes. Sorry for this confusion. Okay. So now let's look at the heat kernel. The fact, yeah, the heat kernel K, heat kernel K is of order minus D. Yeah. Let's try to understand why. So what is K of Z or K of Tx? K of Tx. I mean, if we forget about the fact that we're on the torus, then it's basically 4 pi t to the d half exponential minus x squared over 4t. When can this guy blow up? Well, we have an exponential here with a minus sign, so this guy certainly does not blow up. It's a good term. But here we have something that can blow up. Yeah? When does this blow up? It blows up when t goes to 0 and when the norm of x squared is of order t. So there you again see why it makes sense to use this kind of parabolic norm. Because we want to have x squared of order t. Yeah. So again, so what is this? This is this constant factor t half 1 over square root of t to the d times this exponential x squared over 4t. Okay, so when does it explode? So explodes if what happens? Well, if x, the norm of x is roughly of order square root of t, yeah, which is roughly of order epsilon for epsilon small. Yeah. So what happens in this case? In this case, K of Z is what? Well, if this is true, Here in the exponential, you have something of constant order. The exponential is of order 1. Yeah. So in this case, this is roughly square root of t to the minus d. Yeah. And since x and square root of t are of the same order, this is really roughly the same as zs to the minus d. Okay. And so this explains why it's kernel of order minus d. So it blows up at order minus d. Okay. Other questions about this? No. So I think I have 5 more minutes, but I would need a bit more time to finish these computations. So
Dirk,
yes.
just a quick question, maybe. So, may you just derive in a slightly more rigorous way this this behavior of the kernel using the self-similarity of the kernel?
Yes. Yes, that's how you. Yeah, exactly.
But in principle, what you just explained works also if the kernel is not exactly self-similar, no?
Exactly. Yeah. I mean, if you have the self-similarity, then it's really a scaling argument, which gives immediately the thing. Otherwise, it won't work.
What is self-similarity?
Well, it's essentially scale invariance. So how does it work? I guess if you do something like this, I think this is what it means. So what happens then in this case? So this is the original heat kernel times lambda to the minus d, I guess, or something like this, no? Or d half or so. Should be something like this. Or minus d, I don't remember. Well, I could check. You can also check. No, minus d, of course. Is it this what you mean, Milton, right?
Yeah, yes, yes, exactly what.
Exactly. And in this case, you want actually a similar relation also for the derivatives. And of course, what you could do is you take this function and then you compute the derivatives and you check what you get. But of course, once you have such a relation, then well, you use chain rule to compute the derivatives and the behavior. And get that the more derivatives you take, you always lose one in regularity. In homogeneity, sorry. Okay. Yeah, so as I said, so I think I would need a little bit more time to continue or to finish this computation. So maybe then it's a good idea to stop here and finish it on Friday. Yeah. So I think I would need 15 more minutes, and I think people are probably tired, so it's maybe better to finish it on Friday.
Okay, thank you.
Okay.
Any question, comment? In English, in Portuguese.
Exatamente.
Milton, any questions?
No, not anymore. Okay.
No,
Thank you.
No, I have a question, but not about this lesson. Okay. After read about the reference for the topics.
Okay.
After I imagine the reference is the books of Fritz and Heider, no?
Actually, no. I mean, that's also a good reference.
Okay.
But there's some notes that I like a little bit more because they are much more concrete. I mean, this is a super complicated theory.
Okay.
And there's some notes by A.J. Chandra and Hendrik Weber. I don't remember how they're called. It's something like, well, if you Google for it, then something like regularity structures, integrating party systems, or something like this. I don't remember how it's called, but it's of these two guys. They have really excellent notes. So they wrote these kind of notes in 4 chapters, where each chapter is supposed to be 1 lecture, but Henrik told me that they were never able to give these notes in 4 lessons.
But this reference is good for the first lecture
Yes.
or
Yes.
for the second lecture? I see.
No, for all of it, for everything. For
Okay.
everything what I'm saying, so it's really based on this.
Okay.
Based on that. So I think as a first reference, at least to my taste, is maybe the best reference.
Okay, thank you, Milton. Okay.
Yeah.
Okay.
These are my favorite references. I can send them to you.
Okay. We continue on Friday, 4 o'clock, no?
Yeah, perfect.
Okay. Bye-bye. Thank you.
Bye-bye. Thank you.